Okay, good afternoon, everyone. So just to check, can you hear me? Okay, perfect. Um, all right, so what are we going to do today? We are going to continue and close the chapter on the file system. Um, Again, this is what you're going to do for project 4. Okay, so project 4 is about the file system. It is going to be probably the hardest project in Pintos. So if you're done with project 3 and you want to actually start with project 4, here's my advice to you. Right now, there is a file system, okay, implemented in Pintos. The first thing to do is really understand what's already implemented. And to do that, it's simple. Try to see what's happening when you try to read and write a file. Okay? So, right now you have implemented actually system calls to read and write. You can do that. You can read and write file, but then follow in the code to see what's happening into the file system and understand how the file system is structured. Once you understand that, you're up to a good start. Okay, so it's going to be easier for you to actually start working on the project. Okay, so I think it's actually the hardest part, understanding what's already there. So most of the things that you have to implement, we discussed it last week. Okay, so but again, I'm gonna talk about this concept today. But today, actually, what we're gonna see is some advanced concept on file system. Some of these concepts are actually implemented in our modern OSs like Linux, Windows, and Mac OS, but they are not necessarily implemented in Pintos. Okay, so let's start talking about that. So here we're going to see some advanced concept, and we're going to have two goals. Okay, the first goal we're going to have is we're going to try to improve the performances. Okay, because you will see from the original kind of Unix file system, the performance were pretty bad actually. Okay, and after that there was another file system that came up from BSD, okay, which is also a Unix distribution, and they invented the fast file system. Okay, and we're going to talk about this one here. And the fast file system gave a gain in terms of performances. Another problem that arises is what if there is a crash? Okay, a crash or power loss. So basically, power loss, so the computer shuts down, or actually the OS crash. There is a kernel panic and so on. What if you were in the middle of a write on your disk? If you remember what we did last week, if you're in the middle of a write into the disk, it depends what you are doing. Are you writing a block, a data block? Are you writing an inode block? Are you updating the bitmap with updating what's free and what's allocated? Depending on what you are doing, a crash will have serious consequences. Okay, and they happen quite often. Maybe not actually those days when we have we are working on laptops, we have batteries and so on and so forth. But desktop computers, and actually in the past, this was happening very frequently. Okay, so what do we do in that case? And here we're going to see two approach. One is called the log structure file system, and the other one is journaling, which is actually what's implemented on Linux XT3, but also NTFS actually on Windows. Okay, so we're going to talk about. So first, let's improve the performance of the original file system. So again, what was the original file system in Unix, for example? The disk is divided into 4 pieces. Okay, the first block usually is going to be the super block, and that's kind of to tell how the disk is organized, how the file system is organized, and so on and so forth. So it contains all the data necessary when we boot the computer. We read the super block and we have everything we need. And then there is the free list. Okay, and here last week I told you there are two approaches, right? One which is the one that FAT implements, or actually the original Unix FS, which is have a linked list of the free blocks inside your disk. Okay, and that's actually part of the original file system. We saw after that that there was also the approach of bitmap, and I'm going to talk about that again today. Then you have the inodes, which is actually basically you can think about it as the entry door for all the files. Okay, behind each inode there is going to be a file or a directory, because file and directories are the same on Unix. And it's going to contain all the metadata, like the size and so on and so forth, and all the pointers to the data blocks. Okay, and we have seen that how it's organized with the indexed file system, for example, where you have 15 data blocks, and the last three actually are double and triple blocks. Okay. And then finally you have data block, which is most of your disk, and these data blocks are this is where we store data, right? On the original file system, a block was corresponding to a sector. Okay, I told you a disk is basically a big array of sectors, and in the original file system they had one block equal one sector. So 512 bytes, that was the size of a block. Okay. At first, this setup was actually very slow. Okay, and it got only like 2% of the maximum bandwidth of the disk when you try to read and write file. Even worse, actually, the performance of the disk were degrading over time. Okay, why? We're going to see that. So, not that great. So why was it so slow? Basically, three problems. Okay, at first the blocks were too small. Okay, having one block equal one disk sector, that was actually small. So of course, if you have small blocks, the file index is going to be too large, right? So you are going to have you're going to divide basically your disk into many chunks, and you will have to index all these chunks, right? So that's why the file index became very large. Okay, so meaning the amount of metadata that you use to actually manage all these blocks is bigger. Okay, it requires also more indirect blocks, right? Because remember what we did last week. If you have 15 kind of pointers inside your inodes, if each of them is 512 bytes, very, very quickly, if you have like a big file, you're going to go into the three last indirect blocks, right? And so, and of course, the maximum kind of file size is going to be lower, and the transfer rate is quite low, because we are transferring basically one block at a time. Okay. The second problem is the way we manage the free list. Okay, and I told you at first with the original file system and FAT for DOS, the way it was done, it was a big linked list. Okay, and again, the problem with that, we have seen that with FAT specifically, it's fragmentation. Okay, over time, at first the free list is all like kind of nice and well aligned and so on, but over time, when you create and delete files, this free list becomes hard to navigate. Okay, so that's the main concern. And again, we have seen that actually last week, but I'm going to repeat. The way to solve that is actually to use bitmaps. Okay? And the other thing is poor locality. So last week, and the week before, I think, I told you the following, right? We're going to see the disk as an array of sectors, and that's it. We don't need to know actually how it is underneath, whether we have SSD or hard disk or whatever, right? And we're not going to take that into account. And that's true. I mean, when they created the original file system in Unix, they didn't take that into account. Well, it turns out actually, so in the past, we only have hard disk, okay? So, and I told you, right, the hard disk is like, there is a mechanical kind of arm that, have to position the head and read on the disk rotate and so on and so forth. And they quickly realized that if you don't take that into account, okay, if you don't take into account the geometry of the disk, okay, you will have poor performances. Okay, so that's why it's poor locality. The inodes are far from data blocks. The files that are from the same directory, they are not close to each other, and so on and so forth. And that's bad, because that means that the disk is doing a lot of seek time. Okay, seek operation. We have seen that in the 2 weeks ago on week 7, right? So again, here, if we want to improve the performance, maybe we have to take that into account. Okay, and that's what they did. So the fast file system called FFS was designed for the BSD Unix distribution, and the idea here is like they created a file system which is aware of the geometry of the disk. Okay, so and we're going to see that. And again, this has actually improved the performance quite drastically. So what was the first problem? The problem of like the blocks are too small. Okay, so the fact that you have very small blocks, 512 bytes, which is here one block equal one sector. Again, you know, you're gonna have a lot of blocks. Okay, so that means a lot of metadata to manage those blocks, and here, you know, the time you're gonna spend actually working at the block level, okay, it's actually it's gonna increase. Okay, but so what you can do is like you can increase that. So you're gonna say, okay, you know, we're gonna take maybe let's say 8 sectors. It's gonna be one block. Okay, and then I'm gonna read and write one block at a time. So if you do that, and so for that actually you are gonna have less metadata to manage that, and so on and so forth. So here they have tested it actually, and they realized that okay, actually increasing the size of the block actually improved the performances, right? You can see here from actually 4 kilobytes, which is actually the kind of blocks that we are using right now. It's actually pretty good, and even better if you go to 8 kilobytes, right? So it increased the bandwidth. What's the problem? Here you increase fragmentation, okay, of course, because remember when you allocate a block, you allocate the block entirely, right? And the bigger is the block, if you have a small, very small file, okay, or a file that is, you know, just above the size of a block, well, you need to allocate 2 blocks, and so you're going to waste a lot of space. Okay, so with bigger block comes bigger fragmentation. So how to deal with that? One idea that they had was to use fragments. Okay, so first of all, they had big block size. Okay, 4 kilobytes block, or actually 8 kilobytes. But they allow the large block to be chopped into small chunks that we call fragments. Okay? And so within the block, they had several fragments. And the idea is like, you know, if you have, for example, a file, I'm gonna have an example soon, but if you have a file that is a little bit larger than one block, you know, okay, you're gonna allocate one block, but then you're not gonna allocate a second block entirely. Okay, you can allocate a segment within that block. And so if you have 2 files that are like in the same configuration, what you can do is like you can share this block between 2 files. Okay, so here again, you know, the idea is like, you know, you still work at the level of blocks and so on and so forth, but you know, for the, you know, the small kind of piece that you have for small files, or for you know, the file that is larger than a block, you have this kind of fragments. Okay? And the idea is like you're going to limit the number of fragments you have per block, so it's either 2, 4, or 8. I'm going to show you an example with 4. Okay? The good thing with that is like, you know, if you have a large file, you have a high-speed transfer because you are basically doing it at the level of blocks, right? And you don't waste space for small files. Maybe here something I haven't explained. Why having a bigger block increase transfer? Okay, because at the end of the day, you know, when you're actually on the disk, you're going to write one sector at a time. How come? But the idea is the following: if you allocate a block, you're going to allocate. So imagine that, you know, you have one block is let's say 8 segments. 8 sectors. When you allocate this block on the disk, you're going to allocate these sectors contiguously, okay, meaning next to each other. And if you do that, especially when you have a hard disk, this is going to be fast, okay, because they are next to each other. You know, the time to actually write those blocks, there's not going to be any seek time. They'll be next to each other. It's going to be very fast, as opposed to if your block size is the block of a sector, which is one block equal one sector, you don't have a guarantee that these sectors are going to be next to each other. They're going to be, wherever we have space. And so maybe writing those sectors, will require some seek time on the disk. Okay, so I'm going to talk about this geometry again later. Okay. So what's the idea with the fragment? Okay, so let's imagine the following. We have here a block size which is actually 4 kilobytes, and then a fragment size that is 1024. So basically 4 fragments per block. Okay, and again a sector is half of that. So here would be actually 1 fragment equals 2 sectors on the disk. Okay, but still that's the thing that we have decided. So here you can have this kind of configuration where actually you have a first file, file descriptor 1 here, that's taking 1 block plus 1 segment. And then you have a very small file here that doesn't even take a block but takes 2 segments. Okay, so that's, so far it's fine. Okay, so FD1 is going to be 5 kilobytes here, and FD2 is going to be roughly 2 kilobytes. So what's happened when you try to extend this file? Okay, so let's try to extend file descriptor 1. We're going to write an A. Okay, so if you write A, and assuming that this A is actually the size of a fragment, so 1024 bytes. So here we're going to create another fragment, and here we're going to put it in the same kind of in the same block here. Okay, so then it's fine here, no problem. We have basically one pointer here, and then 2 small pointers to fragments. So then here FD1 is going to be 6 kilobytes. And then we're going to append A again. But then this block is full here, so we're going to create another block. Okay? And within that block we're going to create yet again another segment. But wait a second, here we're starting to fragment the file A quite a lot. Okay? And the idea here is like, you're not allowed to use fragment across multiple blocks. So here we have 2 blocks where we use fragments, and you should only have 1. So what do we do in that case? Well, we copy the old fragments to the new block, okay, and we're going to kind of allocate this entire block here, because here we have a critical size of 3, and it's going to say, okay, fine, now we are going to allocate this block, okay, and now actually FD1 is going to be 7 kilobytes, okay. So that's the idea here. So you're going to use fragment, but at some point you're going to reach some kind of a condition. The file system is going to detect that and is going to copy those fragments. Again, there is an overhead. I mean, for sure there is an overhead when you copy those things, but the fact that you're using fragment, it's still actually a lot faster. Okay. So that actually speed up the disk quite a lot. The other problem is like, how do you manage the free space? Okay. And in the original file system and on FAT actually also, at first it was some kind of a linked list. Okay, so at first you do a linked list like this, so everything is fine, it's all kind of nested, but then over time, it gets worse. You create and delete file, it becomes like kind of a mess. Okay, and they measured actually that when you have a new file system, 17% of disk bandwidth is used to actually 17% of the disk bandwidth is actually they measure the performance and they realize that they can use up to 17%, but then over time it degrades to 3% of this bandwidth. Okay, and that was pretty bad. So here the problem is like having this kind of list and so on, it needs a random allocation of sequential block over time, and they were not able to actually to regroup all these free blocks together or to reorganize the list, right? So one idea is like, you can actually have something that is going to compact or defragment the disk. If you were one of the, in the past, actually, if you were using Windows, I was a Windows user a long time ago. And once in a while, we had to do that with the FAT file system. You have to start some kind of a program called a defragmentation program that is going to actually reconsolidate reorganize the disk, reconciliate all these free blocks and so on together to actually improve the performance of the disk. Okay, and you have to do that once in a while. Okay. or actually there is a better approach here, which is, and again, the other thing is like, maybe you have to once in a while go to this free list, reorganize it, and so on and so forth, right? But it's costly to maintain. Every time you do that, by the way, the disk is working, right? So if you are doing something else at the same time, it's going to be very slow. So the other approach is actually the thing that I described last week, okay? When we talk about the index file system, which is using a bitmap, right? And here using a bitmap, you just keep bits either 0, 1, whether it's allocated or free. And here it's actually easier to find contiguous block, right? You just do some operations on these bits here, and that's it, okay? So it's small, okay? There's no pointers and so on and so forth. So it's small. You can keep the entire things in memory, by the way. It's going to be quite memory saving. But if you have a big disk, okay, you're going to have a big, I mean, depending also on the block size, but even that, if you have a fixed block size, even 4 kilobytes, if you have a big disk, it's still going to take time for you to find blocks, because you're going to have to do some kind of operations on a large bitmap. Okay, so, but in a way, it's actually not bad. Okay. How does the OS detect fragmentation? How does it affect the performance? Actually, the OS doesn't detect fragmentation. Again, the tool I was telling you, you have to kind of, this tool on Windows, I don't know if it still exists on Windows, actually. I haven't used Windows in more than 10 years. But basically it's showing you like some kind of a map of the disk, it's telling you some kind of a percentage saying how many files are fragmented and how much disk space you can claim and so on and so forth. And based on that, you decide or not to launch the disk, the defragmentation, and then it goes on. So, and how does that affect the performances? Well, if the disk is fragmented, so it affects the disk because of the disk geometry. I mean, especially if you have a hard disk, we're going to see that in the problem number 3, and also because this free list here, it's actually harder to manage. So here, for example, imagine if you have to find space for a file that is, I know, you need 1 megabyte, right? So at first, you're going to try to find contiguous block together. So you're going to go to this free list and so on to find the best place, right? And that's actually costly because you have to follow the pointers, right? Remember what I said last week? Every time you have to follow some kind of pointers, it's taking time, okay? As opposed here, actually, the bitmap is actually faster. Sorry. Again, using bitmap, it's kind of simple. You take the bit string, you do some kind of operations on the bit, and it becomes easier, right? And the disk becomes full, the search becomes more expensive because maybe you have to actually go to the entire bitmap to actually find what you're searching. But still, it's better than actually the linked list, right? So here you still trade space for time, okay? So it's going to take time, but it's actually a bit better, okay? Yet actually defragmentation can help in that sense. The last problem that we have seen is locality, and that's actually the one that is going to give us most of the performances. In the first 2 weeks of the file system, I told you, let's ignore the disk geometry. Let's ignore whether it's SSD or hard disk, okay? But in the past, we only had a hard disk. SSD is quite new. And, we're just going to, treat it as a big array, and we're going to kind of have it like this. If you keep it like this, here, you understand the following, right? The inodes and so on, all the bitmaps, it's going to be stored inside, somewhere on the disk. And at some point, what you do always, like when you read, for example, a file, you read the inode and then you jump to a data block. When you write, actually, you write first the bitmap, then you write the inode, maybe, but most of the time you update the inode, and then you write the data block. So you see, for reading and writing, what you do is like, you update stuff here, here, and then you jump there. Meaning the jump, if this block, if the data block is far away from the node on the disk, okay, on the geometry, it's going to take time because you have to move the head, okay? Maybe here, this is going to be like kind of, oops. Remember, right? So for example, if it's here and you have to move all the way here to reach your data block, you have to move the arm, okay, the head. And we saw that last week 7, we saw that this is actually what takes most of the time on hard disks. Okay. So the idea here is like, can we group things together? And we can on the disk actually. So I told you, right? So first of all, when you read one sector here, when you position the head, you also there's only one arm, right? So when you position the arm to read the head and to read the sector here, you also position to read it underneath, here, underneath, here, underneath. And if you have like 3 disks, basically you can read 6 sectors without moving the arm. Okay, so that's one thing. The other thing is like, the disk rotates here. So, as the disk rotates, without moving the arm, you're going to read all the sectors that are on the same track. Remember, there is a concept of track here. So all the sectors around that track, you're also going to read them. So in a way, if you want to minimize moving the head, okay, what you can do is like, you can kind of consider that you can group them together. You're going to group all the sectors per cylinders and all the sectors per track, okay, and you're going to try to keep stuff like this. So if you do that, you're going to create what we call cylinder groups. And the idea is like, you can read many blocks without actually performing a seek. Okay, and you can try to put everything that is related into the same cylinder group, and then putting everything that is not related to another group. So what does that mean? So what does it look like? Again, the idea here is the following. If you access one block, for example, because you are reading a file, most likely you're going to access the next block. So it would be great if those blocks are part of the same group. Okay, so adjacent sectors or actually, kind of on the same kind of cylinder. If you look at an inode, okay, if you read the inode, most likely you're going to look at the data of this inode. So it would be good if the sector where you store the inode, it's also in the same group as the sectors where you store the data blocks. Okay, and also when for example you are working with directories and you read files within a directory, chances are that you're gonna read the same files. You're gonna read 2 files within that directory. So if they are again in the same group, you can access them a lot faster. Okay, so if you do that, how does the OS is going to look like? In FFS, what they have done is they have actually divided the file system into groups, and all these groups are basically a mini Unix file system, where you have actually they have replicated the super block. Okay, so that's actually same thing. Inside the super block there will be information about this group specifically. And here, each group will have its own bitmap to track what's free, what's not. They will have the inode, and they will have the data block. Knowing that all of this here can be accessed with very, very minimal seek time. Okay? Or even none. Right? Because you don't have to move, you just have to either rotate the disk or read the same cylinder. So if you do that, what you need, of course, is some kind of a higher level to say, okay, where do I store what in which group? Okay, so you have a little bit of logic saying, okay, they're in the same directory, I'm going to put them in the same group. They are, the same file, I'm going to try to put it inside group and so on. Okay, maybe you have a large file, maybe you have to split it over 2 groups, and that's okay, right? But you know, most of the files that we have are actually small and they can fit into one group. Okay, that's the idea. So, and that actually had great performance gain, right? So thanks to the file system, they were able to have 20 to 40% of the disk's bandwidth for large files. Okay, so at first it was maybe like I forgot, but 2 or 5%, very very small, and now they were able to actually got 40%. So, and it's basically 20 times faster than the original one. Okay, so so that's why maybe it was actually 2%. And it's stable over time, meaning as the you do operations on the file system and so on, you didn't have performance degradation, which was good. And of course, it's very performant for small files. Okay, the one that are, for example, in the same group, it's going to be very fast. Other thing that they improved, they gave the fact that you can have long names, because at first the name of the file was limited. I mean, all of that didn't improve the performance; it just improved the usability, right? You can also have some parameters, and then there is some space reserved for the admin to actually do all kind of things. I mean, that was optimized for Unix, basically. So that's in a nutshell how the fast file system improved the performances by taking into account the geometry. Now, something important here. They did that because at that time we had hard disks. When there is there is some kind of a mechanical operation. Is this still useful when you have SSD? Probably not. Okay, or probably some of them are. For example, like the bitmap, maybe it's actually faster than the linked list for sure. Okay, but grouping the stuff together, maybe not. But it doesn't degrade the performance for sure. Okay, so but again, nowadays they're actually trying to reinvent some file system that actually a lot faster for SSDs, considering that it's going to be on an SSD drive. Okay, so again, this is still kind of work in progress. There's still a lot of research actually on file system. I can tell you also the kind of research that are there is also depending on what kind of operations you're doing. For example, if you are Google, and you are doing, for example, a lot of read and not a lot of write, all of this stuff, it makes sense to invent your own file system. And they do invent their own file system. Okay, so another problem that we used to have was, we still have actually, but it's how to improve the reliability. Reliability in case of what? In case of a crash. And here there have been like two kind of approach. One is the log structure file system, and the other one is journaling. So let's talk about that. So what happened when there's a crash? So first of all, 2 weeks ago, I told you one thing. When you write, so you write one sector at a time, okay, first of all. And when you write a sector, and the sector is 512 bits, you can be sure that it's written atomically. Okay, so meaning, there is no such a thing as cutting the power in the middle of a sector. You're not gonna have a sector that is half written. That's impossible. Okay, you either write it or you don't write it. But again, it's a sector. It's not a block. Okay, so here when I say that you write one block, depending on the size of the block. But if you have 4 kilobytes block, it's going to be many sectors. So you might write a block and not write it entirely in case of a power loss. That's something to understand. But also, when you do a file system operation, you might modify several sectors and sectors that are completely away from each other, right? So, for example, because you have to modify the metadata first blocks, which is the 3-bit maps or the inodes. And you're also going to modify several data blocks. So overall, if you have a crash, it might corrupt the file system operation that you're trying to do. Okay? And that's a real problem, because the next time you boot, you have a file system that, you have maybe inodes that don't correspond to, or maybe you have written the inode, but the data block haven't been written and so on. You have basically files that are corrupted. Okay, So that's bad. So you need to ensure consistency. Okay, every time you crash, you cannot have a file system that is corrupted. So so how do you do that? I'm going to show you 3 solutions. The first one that they invented, of course, on Unix was, how about I have a tool that if there is a crash, after a crash, when you reboot your system, it's actually going to check the file system. Okay, and maybe repair, if it's possible, by the way, repair the errors. Okay, so the idea is like, you have actually this exists, a file system checker, and then you look at the pointers, you look at the bitmaps, it looks at all kind of things, and it tries to fix error automatically. But you cannot fix everything. Okay, there are stuff where, for example, if you were about to write a data block and you haven't had time, the block is gone. It's not in memory, right? The memory is volatile. So you cannot fix everything. Okay, and it had poor performances because if it's a large disk, it's going to take basically hours to run on a large disk. Okay, so that's not great. And also, when you run it, what do you decide, right? And it was up to the user to actually run it if there was a crash, right? And you have to basically know what are the consequences of a crash to actually understand that you have to run this tool at the beginning, right? But if you are a user that is not very familiar with the OS, you might just reboot without actually running this tool. So it's complicated. So overall, keeping the file system consistent with the way we have been defining, even with FFS, it's not well defined. So we need better things. So the first solution is a file system called log structured file system. We also call it like copy on write logging. So what's the idea? The idea is the following. You're going to treat the disk like a tape driver. What's that? The idea is like when you're about to write something, first of all, you're gonna have everything in memory, and only at the last minute you're gonna write. Once you have everything in memory, you're gonna write. Okay, you're gonna write it in a long sequential log. Okay, so that's why we talk about a data segment. We buffer it, and once it's there, we're gonna write it in long sequential logs, and we're gonna write it on agents and blocks. So it's going to be very fast to write that on disk. And something interesting, the existing data is not overwritten. Okay, we're actually going to write this segment wherever we have a free location. Okay, and all together, by the way, all together, what do you mean? What do I mean? I mean actually here, we're going to write, for example, the data block, and we're going to write the inodes, and we're going to write the free bitmap, and so on and so forth. We're going to wrap everything in there, in the long sequential access, because we know it's going to be fast. Okay. So here, if you follow that, we're completely destructuring our, the good old thing that we have here, right? Even that, even that, we're completely destructuring it because we are just going to write it on the disk wherever we have space, and we're going to write the inode, just after, the data block. So we kind of, throw everything we have done before, in a way. So the question here now is like, okay, we know that there is data, we know that there is inodes and so on, and we keep like, the old and the new version and so on. So many questions here. The first question is like, how do I find the inode table? Because in the original file system, it was easy, right? In the original file system, the inode table is placed at a fixed location. Okay, you basically have the super block telling you where is the inode table. Okay, and you know how long it is and so on and so forth. And it doesn't change. Here, every time you're going to write the inode table somewhere on the disk. Okay, it's completely split and spread out. So okay, so here the log file system, it needs something else that we call an inode map. Okay, what's this? It maps the inode number with its location on the disk. So here, for example, it's going to say, oh wait, you're looking for inode, number 8. Okay, here's the location, and here you see you're going to have several pieces of this IMAP spread all along, right? But again, same thing, you can tell me like it's a chicken and egg, right? How do you know where this IMAP is, okay, for each file? Well, the OS must have some fixed and known location on the disk to begin the file lookup, right? So you boot, for example, your computer, where is the most recent IMAP to know where my inodes are, okay? And here they call it the checkpoint region, and here they still use, you know, the kind of the first, or maybe not the first because it's a super block, but maybe the second, to actually store this checkpoint region, what they call. And this checkpoint region has a link to the IMAP, okay? But you're gonna tell me, wait a second. So when you put a new IMAP, we need to update the CR, which is completely defeat the purpose, right? Because what if there is a crash in between, right? What if there is a crash when, you know, you build IMAP and, you know, you don't have the CR? Well, let's see. We're going to look into that. But here, actually, to not degrade the performances, we're going to update the CR only periodically. We're not going to do it on every write. So here you can write a lot of stuff on the disk. Okay. Again, it's kind of keeping logs. You write everything, but you're going to update the CR maybe only every 30 seconds to avoid degrading the performances. Okay, so it's kind of weird, but actually it works. So let's talk about a crash. What's happened when there's a crash, right? So here, so maybe here, let me start actually with the last line, okay? So if you keep adding the logs, what I call the logs is basically like, you know, you need to have a write operation, for example. Okay, fine. You're not going to overwrite what you had somewhere and so on. You just write it somewhere free on the disk, right? It doesn't matter. You just write it there. So here, if there is a crash, you know, the CR is going to point to the latest kind of IMAP. Meaning, if there is a crash and the CR has not been updated, you can consider that this log is lost. Okay, so here, potentially, you have lost up to 30 seconds of data, which is huge, by the way. It can be huge. Huh? But, you know, that's a trade-off, and they have decided to do that. And by the way, there are ways actually to maybe update the CR, and so, I mean, to still recover the data you have lost in 30 seconds, but at least, you know, we guarantee you that more than 30 seconds, you know, for sure, nothing is going to be corrupted. Okay? I mean, you're not going to corrupt file, okay? With the original Unix file system, it's bad, right? You can corrupt the file and you know, not have a way to actually recover it. Here, at least, you're going to recover your file as it was 30 seconds ago, at max. Okay, so that's something it provides. But then you're going to say the following, right? So if you update the CR, it must be updated atomically. Meaning, what if there is a crash in the middle of you updating the CR? Okay, and the CR is more than just a sector, right? So here it's going to be a big, I mean, probably a block and so on. So what if there's a crash in the middle? Okay, so to do that, here is how LFS does it. LFS keeps actually two CRs, okay? And when it writes one CR, it's done in 3 steps. First, it writes the header, okay? And that's atomic, it's actually one sector, okay? So it writes the header with a timestamp. So you put a timestamp there. And then it writes the body of the CR. Okay, so here the body actually can be more than one sector. So, I mean, this is not atomic, but it writes the body of the CR. And then it writes one last block with another timestamp. Okay, so we have 2 timestamps here. So if there is a crash in the middle, you can detect it. Why? Because the timestamp number 1 is going to be after number 2, right? If you haven't completely returned the CR, you know, this timestamp is going to be older than this one. I mean, it's probably going to be the older version of it, right? So here you can detect that there was a crash. And so what happens if there is a crash? Well, you're going to ignore the CR because the CR has been corrupted. Instead, you can take you choose the other one, okay? So that's why LFS, we always choose the most recent and valid CR. Okay, so if one of them is corrupted, okay, fine, we choose the other one. Okay, you cannot have 2 corrupted because you're not going to write, you know, the two CR at the same time. You're going to alternate, right? At instant 0, you're going to write CR1. At 0 plus 30 seconds, you're going to write a CR2. And then, at 1 minute, you're going to write CR1 again, and so on and so forth, right? So, and thanks to that, this file system guarantees that, you will be able to recover your file in case of a crash, at least as it was 30 seconds ago. Okay, and that's actually way better than what we used to have. Okay, and it's actually fast. Okay, because you write everything actually in sequential blocks and so on and so forth. So it has very good performances. Something that you might also question is the following. Okay, if we keep, imagine you open a file and then you update that file, you write it, and then you save it again on the disk. Here, with what I told you, you're going to have two versions of this file on the disk. Okay? And, when you keep track of the space allocated, the old version is also taking some space. So what you would like to have is once you have the new version of the file, okay, or the blocks and so on, it's going to be actually at the block level, not at the file level. You are gonna you can actually erase the old version, okay, and reuse it for something else. So here with LFS, you need to do a little bit of disk cleaning, okay, and the way it does that, it's actually keeps track of the version of each segment that runs, and it has a disk cleaning process to clean up all the old versions of the segments. Okay, so it goes through all the old versions and so on, and it basically free up the memory, right? And the disk cleaning process actually run not when the disk is active. Okay, if the disk is doing a lot of operations, it's gonna to avoid degrading the performances, is going to let it do it. But then as soon as the disk is going to be idle, there is going to be this cleaning process that is going to start and then run, right? So, So it's going to run, when the disk is idle, or of course, when you run out of space. If at some point you run out of space, it's actually kicking in to make sure that you can do all your operations, right? So we call that disk cleaning or garbage collection, it depends. So that was actually a log file system, which actually has good performances and works well. There is another approach called journaling. And again, this is actually the approach that modern OSs use, especially Linux with ext3 or Windows with NTFS. The idea here is the following. When you're about to write data on the disk, okay, what you're going to do first is you're not directly going to update. So for example, you need to write a file, okay, you need to modify a file. You're not directly going to modify the file, but you're going to, it looks like the logs in a way, which is you're going to write it somewhere else on the disk. And we're going to write it on somewhere we call a journal. Oh, sorry, it's here, okay. So that's why you're going to write ahead. You're going to keep a log or journal. Okay, this is actually what databases were doing, to avoid when you have a crash and so on, and you push something into the database and you want to lose it, or you modify something in the database. What you do first is you write it somewhere else, in a place we call journal. So if you have a crash, okay, what you can do is the following: you can look at and of course once it's written on journal, you can actually update now your file. Okay, it's not like the previous one where actually we never overwrite the existing data. Here we do, but first we kind of write a copy just in case. So when a crash occurs, you can actually restore the data, right? You can go to your journal and say, okay, what has not been written yet? And you can write it again, right? And for that, actually, even if your file is corrupted, you can actually recover it, okay? So you can use the content to actually fix the file system, and this process is called recovery. So let's have some examples. This is how Linux ext3, ext2, and actually ext3 is working. Okay. So there are several approaches. One, you have actually a physical journal. Okay, you write all the real blocks and update the log. And the idea is the following, right? So first you commit the blocks that have been modified, the dirty blocks, to the journal as one transaction. How do you do that? Well, you write first like a tx begin. It's like some kind of a timestamp actually. It's the same idea as the CR the CR in previously. You write the inodes, you write the bitmaps, you write the data blocks, and then you write a commit record with tx end. Once you have done that, you have committed the change. A little bit like on Git, you commit the change. And then once you have done that, okay, fine. Now you have actually recorded your transaction. Now you can copy the dirty blocks to the real file system. So here you're really going to update the file system, which wasn't the case with the previous solution, right? Once this is done, you do a checkpointing saying, okay, done. And now you can reclaim the journal space, meaning you're going to erase your log, right? Because once it's in a file system, that's it. If you have a crash, it's safe, it's actually there, okay? So you reclaim the space. You have another approach, which is logical journaling. You only, you write on the logical record. So, I mean, here, you can say, for example, okay, you keep it as a file, okay, we are going to add an entry F to directory D and that block and so on. But usually we use physical journaling. That's what ext3 is actually using, right? This is faster because it saves on disk and so on, but it's actually better to keep track of everything. So what if there is a crash? Okay, so you do a recovery. The recovery, what you're going to go is like, you go to the logs and you redo all the operations that have been successfully committed to the logs, but were not, or you have a doubt whether it has been written on the disk, right? So you can redo that. So if there is a tx beginning without a txn in the log, what do you do? So let's see. If you have that, it means that there was a crash when you were writing the log. So what does that mean here? Well, your log is corrupted. So you cannot even modify the files. But the good news is your file system is not corrupted, right? Because first we write the log, then we write the file. So here, it's fine. You're just going to ignore it. So here you have lost maybe this transaction, but your file is not corrupted. If txbegin is there through txend in the log, it means that everything is fine. I mean, your log is healthy. But if it's there, okay, and it has not been checkpointed, okay, which is this step here, it means that there was a crash in the middle of updating the file system. So what you can do is like, you can reuse all this information to actually redo that operations on the inodes, the bitmaps, and the data blocks, okay? And so here you're basically repairing the thing. So here, if you can see that, you have your log and it has been checkpointed, okay, meaning, you have some kind of a tick mark that says, yes, it has been done, but it's still there, okay, because it has not been reclaimed, it means that the crash occurred after the update and the file system actually has been modified. So here what you can do is like, you can just actually remove the log and that's it. You have nothing to do, right? Because it has been checkpointed. So everything is fine. Okay, so you see here how you can recover from the crash. So it's actually better than the log. That's why they're using it, right? Because you are not losing 30 seconds. You're losing basically maybe the last operation. Okay, or I mean, most of the time the operation going in concurrently, but you're just losing the latest operations, as opposed to 30 seconds of work, which can be used. Okay, can be huge. But again, journaling has a cost, okay? Because you are doing one write, you write to a journal, and then you write on the file system, as opposed to the log structure file system where you just write and that's it. You have nothing to do, right? The other one, you have a cost of managing the inodes and so on, but you don't have to update. So here actually journaling is a little bit slower than maybe log. But overall, that's the best solution. That's the most reliable one. Okay. So again, if you have to do 2 writes, it means maybe you have to do 2 6 if you have a hard disk, and that's actually what takes time. There are several modes actually I mean, ext3, you can basically configure it. You can say, for example, you can just do data journaling. Okay, so meaning you write everything to the journal, inodes, data blocks, and so on and so forth. On metadata journaling, you can write only the metadata. Okay, so here you can maybe restore the inodes and so on, but the data are going to be lost. Okay, so that's why the file might contain garbage data, but at least your file system is intact, right? So here you are going to have a gain in terms of performances, but you might lose data, but you're not going to corrupt the file system. Or you're going to have the ordered mode. Where you write data to the real file system first and then journal it. Okay, so this is actually how ext3 works. Okay, so and then you can always if there's something wrong, you can actually repair your journal with the data, which is kind of like weird, but actually it works. So that's it. I mean, again, all this stuff, you don't need to know them for Pintos, okay? But it's good to keep that in mind, right? In Pintos, for example, you're gonna do that without taking into account the disk geometry. You're gonna do it without taking into account crashes. If it crashes, it's gonna corrupt the file system, okay? But if you were to take Pintos, for example, to the next level, this is the kind of stuff you would implement. Okay, so I don't know, if I had an advanced course in operating system and I still want to use Pintos, I can have a project where implement a journaling file system, for example. Okay, and so you can do that, but at least for what you have, you don't need. But again, what's important is going to be, I'm going to go back to my page with bitmaps. Oops, went too far. Okay, this idea of like using a bitmap here, okay, that's going to be important, right? Because that's, I mean, it's already implemented like this, by the way, and you have to understand it, because you're going to modify it, and that's what you're going to use. Okay. Are there any questions? You were very quiet. It's not many of you, only 20. Okay. It's the end of semester. We all start to be a bit tired. I understand. But do you have any questions? Are you still listening at least? Okay, good. Yeah, okay. Great, thank you. All right, no questions. So again, we are done with file system. I might talk again about file system next week, because I know next week it's going to be the right time to talk about more into detail about project 4. So we'll talk a little bit about that. But as of today, I've covered everything I wanted to actually, all the main stuff. I mean, the file system, virtual memory, threads, threading, multi-threading, user space, and so on and so forth. All the stuff that you're doing in Pintos. So I still have 3 lectures going on. And these 3 lectures, I'm going to try really to open the scope of the course by talking about very modern stuff. Like, one is going to be security. One is going to be mobile computing, cloud computing. And the last one, I'm also going to talk about virtualization. And I'm going to try to talk about like more, maybe address like more like Linux, Windows, and so on, how they work and stuff like that. Okay. All this stuff, maybe they're not going to be useful for Pintos directly, but they for sure they will be at the exam. Okay, so make sure to actually follow those lectures. Okay. All right. So if there is no question, I will end the lecture here. Again, office hours tomorrow if you have questions about project 3, and good luck with the end of the project. Okay. Have a nice day, everyone. Bye.